about the fact that this is a graduate course. I've never given a graduate course before, and the department hasn't really had all that many. I mean, it has them from time to time, but it's trying to make graduate courses more of a feature of departmental life. So it's sort of up to me to interpret what graduate course means, I think. And the way I want to interpret it is that it'll be very different from Part 3 lecture in the sense that I won't feel the need to be totally formal all the time. Actually, just as a matter of interest, are there Part 3 students here? Yes, now it occurs to me that if I were a Part 3 student in the summer term, I wouldn't want to be spending time reading my notes between lectures in a graduate course. So I'm going to try and do things. I mean, graduate sort of sounds more advanced than Part 3, but I'm actually going to try and lecture things in a less advanced way, in a way that makes it as easy to understand as possible, and to go more slowly than I would go if I were lecturing in Part 3. Having said that, there are two theorems that I very much want to talk about. One is the famous theorem of Rasburov about monotone circuit complexity. I'll tell you what all that means later on. And the other is Peter Shaw's algorithm for factorizing using a quantum computer. And the actual proofs of those theorems I do want to give in full, so I'm not going to be informal when it comes to those. But the background, sort of saying what circuit complexity is and that kind of thing, I won't necessarily write everything I want to. Sometimes I'll define the concept just by giving you an example of it, and then it'll be pretty obvious what the concept is, and that kind of thing, something that would not be really legal in a Part 3 course. So, actually this lecture will be particularly informal, and particularly unnecessary to remember for the rest of the course. So I'm going to start by talking about, not for the whole lecture, start by talking about what a Turing machine is, very informally. But the main aim will be to try to convince you that we don't have to think about Turing machines for the rest of the course. But somehow I feel that you have to start with Turing machines because that's what everybody understands by computability, or there are different ways of understanding it, but they're equivalent to Turing machines. So let's just remind ourselves, I hope most people have seen some kind of account, maybe in a popular maths book or something, of what a Turing machine is, but let's just have a quick reminder, as I say, very informal, of what they are. So, the elements that you have of a Turing machine, you have a string of noughts and ones, which is usually called a tape. You have this picture of a little actual machine moving up and down a piece of paper that's got some noughts and ones on it. So let's just represent that by some asterisks. Each one of those is a naught or a 1. And the Turing machine itself is a little sort of thing, device, that's in some kind of state, which we might call SI, and it's pointing at one of the places in the tape. The Turing machine can be in any one of states, let's say S0, where it's starting state up to SK. So what happens at a particular stage of the computation? Well, SI has a sequence of instructions. And what the instructions tell you to do concern what the bit is here, what state the machine should be in, and where it should be at the next step. So SI might say something like, if this is a naught, change it into a 1, move to the right by 1, and change the state of the machine to SJ. Something like that. That would be a typical instruction that SI might have. And then it would also have to say, oh no, sorry, it should also depend on this bit. So if this bit is a naught, change it to a 1 and move to the right and change the state J. If it's a 1, stay put and change the state H. Something like that. That might be a typical instruction of SI. So SJ or SH would be some other instruction. What it doesn't know, for example, SI doesn't know something like, I am in position 4 along this string. All it sees is very, very local. So if you want it somehow to know where it is, you've got to encapsulate that somehow in the state of the machine, or to have written some little information on the tape that will give you information like that. Let's have a very, very simple example of the Turing machine. It's so basic that it doesn't actually illustrate in full generality what a Turing machine does. But supposing you wanted a machine that would take a string of ones and tell you at the end whether you've got an even number of ones or an odd number of ones. Nice, easy thing to do. So here's our string. So we start in state S0, pointing at this bit here. And then S0 could say, if you see a 0, then change to a state that just says even. And if you see a 1, then go from if naught, this is S0's instructions. If naught, then go to state which we call the state even, and just stop, you've finished. If 1, then go to state S1 and go right by 1. And then S1 is the same, except if naught you output odd, and if 1 you go to state S0 and go right by 1. So what does the machine do? It starts in S0, it sees a 1, so it goes 1 to the right and changes to state S1. And then it keeps on going until eventually it reaches the end of the string and sees a 0, and it now says, oh, am I in state S0 or S1? If I'm in state S0, I'll say it's an even length, and if I'm in state S1, I'll say it's an odd length. And it's done the computation. So I suppose the thing that was not completely general about this was that at no stage did I actually rewrite any of these ones as noughts, and you can do a lot more if you're allowed to rewrite ones as noughts as you go along, or noughts as ones. But at least it gives you a rough idea. Now, let's start the process of eliminating Turing machines from the discussion. I want to make the observation, well, let's just see what, let's just think of a way of encoding what's going on at a certain stage of a Turing computation. So, first of all, let's suppose we're going to be talking about complexity, and so we're going to be talking about computations that stop after some certain predetermined amount of time. So if you're just interested in arbitrary algorithms, you may be interested in algorithms where you've absolutely no idea when they'll terminate, and you can't say anything about that. But we're going to be interested in things like whether an algorithm terminates in time polynomial in the length of the input. And if that's the case, if it does terminate in time polynomial in the length of the input, then it cannot move more than a polynomial distance from its starting point, so you might as well just restrict your attention to a tape of polynomial length. So I'll only be interested from now on in finite tapes, where the usual model of a Turing machine is that you've got an infinite tape, and in principle it could go arbitrarily far. So if we want to encode what's going on at a certain stage of the computation, then we could do it as follows. We have a whole lot of bits, let's say polynomial in n bits, that tell you what the tape looks like at this particular stage of the computation. But we also want to encode the Turing machine itself. We don't want to have sort of start drawing boxes with SIs in them and that sort of thing. But there are only k possible states. So with log k further bits, we can encode what state we're in. You can just, all I'm doing there is just saying I'll number the bits, number the states, 1 to k, and write down the binary representation of the number that represents the state that we're in. So that's Pn bits for the what's going on in the tape, and then let's say log 2k, perhaps I want some upper integer part or something, bits that give you the binary representation of the state that you happen to be in. Sorry about this near overlap. And one other thing is that we want to know which position in the tape the Turing machine is actually pointing at a particular stage in the computation. And so we have another log 2n bits here. So this is that's the tape, that's the state, and that's where the machine is. point is that with just a tiny bit more than n bits, you can in some way encode where you've got to in a computation. And now, let's think about how we get from this stage of the computation to the next stage of the computation. Well, I'm going to get another sequence like this, and how's it going to relate to this sequence? Well, it's going to be precisely the same as this, except that in at most one bit, I'll have changed a 1 to a 0 or a 0 to a 1. And then over here, I could completely change what state I was in. I could go from some string of length log k to another string of length log k. And the position would change by adding 1 or subtracting 1 or adding 0 to the binary representation of the position of the Turing machine. So I get some other sequence that starts off, maybe I've just changed this 1 to a 0 and then everything else is the same. So this is the new position, the new state, and the new, the new state of the tape, the new state of the machine, and the new position. So 1, 1, 0. So ending in a 0, 1 instead of a 1, 0, because it happens to have moved 1 to the left. Now let's just think about how each of these bits of this new sequence depends on the sequence up here. So if I want to know whether I get a 1 here or a 0 here, what do I have to look at? How much of this stuff do I have to look at? Well, the most important thing to look at is this sequence of log 2 bits here, because that will tell me whether the Turing machine is actually pointing at this bit. If it's not pointing at this bit, I know that it will be the same as it was here, which is the case in this instance. Actually, it's slightly unrealistic that I've changed the 4th bit, because that clearly isn't the binary representation of number 4. But maybe I'll just correct that. There we are. Just to make it look more realistic. And then similarly, this one, I just look at the position, I see immediately, just from the position, the fact that it's not pointing at this 0, that I'm not going to change that 0. This is a more complicated one. This is a 1, and I look over here and I see, this number is 4, it really is pointing at me, help, maybe I'm going to have to change. Now what else do I need to know about to know whether I have to change? Well, all I have to know is what state of the Turing machine I'm in, because I know that it's whether or not to change depends just on the state of the Turing machine. It's some function of what state you're in, and this bit here. So the point is that each of these bits here in the new sequence of the tape on the tape depends just on one bit of the old sequence of the tape and these bits here, log 2k plus log 2n. Also, I've got to check that these bits don't depend on too much. Well, these bits depend, what state I'm in will depend just on, hang on, actually I've just realised it's slightly more complicated than I remembered. I will have to look at the position and create a number of auxiliary functions with these. Do I want this? I've just realized that when thinking about this, I've oversimplified slightly. Because in theory, you could say that the state depends, well, it depends on just the position variables and then some sort of variable bit along the tape here. So it's not just on one fixed thing. So what we could say is that we can build it up as follows. We can build a sort of sequence of I've got to come up with some dodge for this.
Could you set up the tape so that the position of the Turing machine is fixed and the tape slides back and forth, and lose your position indicator? With that?
I want to get it as a sort of binary.
Because then you're only depending on the thing that's actually at the head. And each new bit only depends on the thing at the head, so you look at it and the things on either side.
Yes, okay, so maybe that's the best way of doing it then. So I could...
You need an infinite tape for that though?
No, because everything's going to shift by finite. Okay, that's maybe the simplest. That's not what I did when I lectured this a few years ago, but I think that is a simple thing. So then, it's not quite the case that the way that tape depends on the previous tape is as simple as it was before. Each position here is going to depend on sort of the ones to the right and to the left or something like that. So, so that way I can just shift the whole thing. Okay, so that makes life a bit simpler. But this is, the main point is, there is a way, and I think we've just sort of sketched what it is, of presenting it so that each bit of the encoding of where the computation has got to depends just on roughly log n bits of the previous stage of the computation. So we can have a little slogan here, which is, let me write this out, a Turing computation is an iteration of a very simple Boolean function from 0,1 to the m to 0,1 to the m, where m depends in some polynomial way on the size of the input. So the answer to that question about doesn't this require you to have an infinite tape is that you might have a few zeros on either side that slip off and slip back on again, something like that, so that the length remains finite. So very simple, we can talk a little bit more about that, but very simple basically means that each bit depends on not too many bits of the previous string of zeros and ones, at most roughly log n bits. So now let's leave that aside for a second, and so we will see later on why this observation enables us to change our model of computation to something completely different, and that's called a circuit model of computation. So I'm wondering whether this is just to start with an example. I think I'm going to start with an example. So supposing I've got an element of 0, 1 to the 2. In other words, I've got a 0, 1 sequence of length 2. Let's say it's 0, 1. I'm allowed to use things called AND gates, OR gates, and NOT gates. So what's an AND gate? An AND gate takes, let me just say, AND gate is 0, 0 goes to 0, 0, 1 goes to 0, 1, 0 goes to 0, 1, 1 goes to 1. So you put a 1 here, if and only if you've got a 1 and a 1 on the left-hand side. So that's, and it's denoted by an AND sign. An OR gate is what you'd expect from that. This time you put a 1 there, if and only if that's a 1 or that's a 1. And a NOT gate is simpler still because it's just from a 1-bit string to a 1-bit string. So that just changes noughts to ones and ones to noughts. Now let's see if we can use AND gates, OR gates and NOT gates to calculate the parity of this string. So the parity of this string means 1 if it's odd and 0 if it's even. So what I'll do is, the way of getting it to be odd is if either that's a 0 and that's a 1, or that's a 1 and that's a 0. So let's put in a couple of NOT gates first of all. That makes that into a 1. So I'm trying to produce a computation that will work not just for this particular input string, which would be quite easy, but will work in general. So, I'm putting in the values here just to see what happened in this particular case. So here I'll also record what the not of it is. Perhaps I won't put circles around there, just to distinguish between the gates and the values. And then the two things that I want is either I get that and not this, so that means I have to put an AND gate here and take the output, which in this case gives us a 1. Or I get this and not this, which I did not get in this case. I get 0. And finally, I'm allowed either this to happen or this to happen, so I put in an OR gate. And out comes a 1, because it really was the case that I either got a 1 there or I got a 1 there. So let's just see why this circuit does the job in more generality. So we've got an arbitrary bit here. It could be a 0 or a 1. It could be a 0 or a 1 here. So when will this be a 1? Only if that's a 0. So this basically, that will be the opposite of this, and that will be the opposite of this. This thing will, if I get a 1 over here, so because let's put some squares around there, because otherwise it doesn't look very clear. So when do I get a 1 here? Only if I've got both a 1 there and a 1 there, which is the case if and only if I get a 1 there and a 0 there. And then I get a 1 here only if, or if and only if, I get a 1 there and a 1 there, which means I get a 1 there and a 0 there. So I've picked out the two cases I want. I either get 0, 1, or I get 1, 0. And finally, either of those is allowed. That's why I put this OR gate here to get a 1 at the bottom. So now you've seen a very simple circuit for calculating the parity of two bits. And what about the parity of 4 bits? Well, what you could do is this. Let's do 8. So I've got some inputs. And I can just encapsulate this circuit here by what's called a parity gate. So I just call that I'll call that plus like that. So it's a mod 2 sum of what I've got above. So I just stick in a parity gate there, a parity gate there, a parity gate there, and then I just carry on this process. So I've just established, so why is this working out the parity of this sequence? Because if I've got an odd number of 1s here, then there must be an odd number of pairs such that I've got an odd number of 1s. And then I can iterate that argument, which then means that the thing that comes out here will give me 1 if I've got an odd number of 1s to start with, and a 0 if I've got an even number of 1s to start with. And then if I expand each of these parity gates back into this funny circuit here, what I've shown is you can develop this easily into a proof that if I want to work out the parity of a string of length 2 to the k, I can do it with a number of gates that's linear in 2 to the k. That's sort of 1, 2, 3, 4, 5, 6, 7, 8, about sort of 10 times the number of inputs. Now, so what is a circuit? A circuit is anything like this, basically. Or a binary circuit is anything like this. So you start with some inputs, and actually this one is not so representative because this one's in the shape of a tree. That's rather special. But this one's not in the shape of a tree. As you can see, it's got some cycles in it. So, but it's directed. So you have a sort of directed graph like this, with some vertices. And each vertex has degree either 1 or 2 going upwards. If it's got degree 1, then it's you know it's a NOT gate. If it's got degree 2, it's either going to be an AND gate or an OR gate. You put something like a whole bunch of these things together, and right at the bottom you end up with a single bit, which is the output. If you want to think about computations that take an n-bit string to an m-bit string, you're very welcome to have lots of outputs, but it doesn't actually make too much difference, because if you can work out any given bit of your output, then you can work out the whole output. So in other words, you can think of a function from 0,1 to the n to 0,1 to the m as m functions from 0,1 to the n to 0,1. And this circuit is said to compute a given, so a Boolean function is a function f 0,1 to the n to 0,1, and a circuit is said to compute a given Boolean function if the function you get here by putting together all these AND and OR gates is indeed the function f. So that's that, and I've just shown you how you can use circuits to compute some quite natural functions. Let me now just give you a totally trivial lemma that says that every function can be computed by some Boolean circuit. So supposing I've got a function f because it's such a general result, the proof is a little bit disappointing, but you should expect that. So how are we going to do it? Let's just do it in little steps. Let's build up some circuit tools. So the first thing we'd like is to be able not just to work out the AND or of 2 bits, but of n bits. That's easy enough. So if I've got n bits here, and I want to have a bit here that's 1, if and only if all of these are 1s, then I just put together some AND gates. And I continue to AND, and keep going until I get down to the bottom there. How could this possibly be a 1? Well, only if the two things above it were 1, which can only be the case if the two things above those were 1, and so on. And if I haven't got a power of 2 up here, I just, some of them just do this sort of thing. So that's, I'm not relying on it being power of 2 either. So it's easy to produce a sort of more general AND gate. People talk about unbounded fan-in. So the fan-in is the number of things that is the degree of the vertex going upwards. So an AND gate with fan-in k gives you the AND of k bits just above. I think I won't bother with that terminology. And of course you can do the same thing with OR gates and get an OR of as many things as you like. And now if I want to build a circuit to compute a given function, all I have to do is I start with the inputs, and I now have a whole, let's say there are n inputs there. I'm now going to define 2 to the n more nodes on the circuit. Actually, sorry, one step just before that, I will take the knot of each one of these. And now for my 2 to the n things, what I'll do is I'll choose every possible combination where I choose either an input or the knot of that input. So this one here, I will choose the inputs in every single case and do a massive great AND. So I won't draw too many of these, but that one there is the AND of all the original inputs. The next one would be the AND of all the original inputs except the last one, where you take not of it and so on, and you get to go through all the 2 to the n possibilities. So now I think about this function. I say, supposing I want f of 0, 1, 1, 0, and the rest noughts to be a 1. So this is going to be, so that's going to be one of the things that gives me 1. So I'll look at 0. So here's something that I want. Here's a string that I want to give me a 1 at the end of the circuit. How do I make sure that it gives me a 1 at the end of the circuit? I look at all the knots for the things where I've got 0, and take the bit itself when I've got a 1, and take the AND of all those, and the result will be some node here that's 1, if and only if I've got that precise bit string. and then I just look at all the bit strings that are supposed to give me 1, and take the OR of all those. And there's my circuit that will compute the function. That's exactly what I did in the parity case, as a matter of fact. So just have a look back here. I said the two strings that I want to give me a 1 are 0, 1 and 1, 0. So let's take a couple of knots, and let's take ands to pick out. This one picks out the string 0, 1, and this one picks out the string 1, 0. And I take an OR of those. So you've already seen it in action. If you just generalize that proof to an arbitrary function, you get this enormous circuit here. Circuits of exponential size are not considered all that useful. That's the whole point about complexity. You're trying to look for polynomial size circuits or computations that take a polynomial length of time. I'll be talking a bit more about that. But this particular observation, trivial though it is extremely useful for the discussion of Turing machines earlier, because if you've managed to organize your computation so that each bit depends on just logarithmically many bits up here, then you can find a circuit that depends on exp of logarithmically many, has exponential in logarithmically many gates. In other words, it only has polynomially many gates. In fact, a polynomial is pretty good because this log 2, it'll be 2 to the log 2 plus some constant. So it's actually going to be, I think, just a linear number of gates needed. So what am I saying here? I'm saying that each bit here can be calculated from some selection of the bits here using a circuit that has only polynomially many gates, or linearly many gates in fact, but all I really care about is polynomially many gates. So in other words, what I could do is I could say I've got a string of inputs that represents the state at the kth stage of the computation, and I've got a string of inputs that represents the state at the k plus first stage of the computation. And each bit here, I've got about one bit here and some bits over there, and I devise a little circuit that gives me this bit from that combination of bits from the sequence above, so that the total number of gates that I've used here is just a polynomial. Now all I've done there is actually get from one stage of the computation to the next stage of the computation. So it doesn't look too good. I've just used quite a big computation just to do one step of the Turing machine computation. But that's not too problematic, because if the Turing machine computation takes only polynomially many steps, then I've got polynomially many gates, polynomially many times. So the total number of gates is polynomial. So the point is, to get to the next stage of computation, I've got some more circuits down here, and then the next stage I've got some more polynomial sized circuits. In fact, I've got a polynomial, I'm iterating this twice. I've got a polynomial sized circuit for each of these polynomially many bits down here, and I do that polynomially many times. That discussion actually illustrates one of the nice things about why people talk about polynomial complexity. It's because the polynomials are nicely closed under addition, multiplication, and composition, which means that it's a very robust model. You can sort of do things with polynomial computations or modify them in various ways, and they will remain as polynomial-sized computations. So it's a very useful model in that respect. But as many people point out, if you've got an actual algorithm that takes time n to the 100, it's not going to be very much use to you. So it's useful, very, very useful as a theoretical model, and it does tend to be the case that if you can find a polynomial-sized algorithm, then somebody else who works a bit harder can turn it into an n-squared algorithm or something. Of course, there are lots of exceptions to that, but it does seem to be a very good model. Why am I interested in that? Because what that shows is that if there's a Turing computation that works in polynomial time, then there must be a circuit of polynomial size. Because I've just shown that what the Turing machine does to get from stage k to stage k plus 1 can be simulated using a circuit with only polynomially many gates. So any function that's Turing computable in polynomial time can be computed by a circuit with polynomially many gates, but the polynomial for the number of gates for the circuit will be possibly quite a bit larger than the number of steps of the Turing machine. So that's an informal description. I see one puzzled look, so let me just try and say it once more. So if I've got a Turing machine that's guaranteed to give me the output I want after some polynomial number of steps, then I can represent what it does at the kth step using a circuit of polynomial size. There are only, or using, say, you could say using a whole bunch of polynomially many circuits of polynomial size. There are only polynomially many steps. So I put that all together, put all these circuits together, I get one big circuit that just does precisely what the Turing machine did in its computation. And so that means that, let's say, I'll write every efficient, meaning in polynomial time, Turing computable function can be computed efficiently by some circuit. Let's just think about the converse to that. There's no reason to suppose that the converse is true, because we could have just stuck completely different circuits. Yeah, one circuit here, a totally different bunch of circuits here, a totally different bunch of circuits here, and there's no reason. So there's something about a Turing machine, it's sort of doing the same thing at each stage. That is not the case for a circuit. So at each step of the Turing machine, you're doing the same thing in the following sense. You can just, well, you can describe an algorithm in a finite amount of time, and then you just say do that sequence of instructions over and over again. Of course, what you're doing looks different from time to time because what you've got written on the tape is different. But the set of instructions is, if you've got this, then do that. If you've got this, do that, and so on. That is the bit that remains constant, and it's just being iterated. But with a circuit, there's no particular... This notion of iteration of something simple isn't happening. You're just doing lots of very simple things over and over again, but what you do that's very, very simple can vary with time in totally arbitrary ways. What people sometimes say here is that the Turing computation is a uniform model of computation, whereas a circuit computation is a non-uniform model of computation, because you're losing this idea of doing the same thing every time. Nevertheless, there don't seem to be examples of I think you can do some sort of stupid counting argument or something to think about that, to come up with, no, maybe not. Depends how large you allow your Turing machine instruction set to be, actually. So if your Turing machine has to be something that's physically buildable, so there's some absolute bound on the size of the Turing machine, but not necessarily on the size of the input to the Turing machine, then you've only got some finite collection of Turing computable functions, if you want to think of it. Well, that's not a very good way of let me just go back to what I was saying, which is there's no reason to suppose the converse is true, but in practice it seems that anything for which you can find a polynomial-sized circuit, you have to describe that circuit somehow. It's very hard to describe it in a way that you can't then convert into an actual algorithm for computing the function. So the two models are technically different, but 2 points. They're sort of morally equivalent in some sense. And the second point is that definitely Turing computable functions are circuit computable. Now what's the implication of that for complexity theory? It is that if you want to prove that a function is not Turing computable, then it's sufficient to prove that you can't compute it by means of a circuit. Now why is that a good thing to be able to say? It's because Turing machines are rather sort of horrible. It's got this sort of word machine. It doesn't really feel like maths. It feels more like computer science. Whereas a circuit, well, actually circuit sounds a bit like sort of electronics or something. But let's get rid of the last vestige of the physical world and turn it into a piece of maths. I want to convince you that the question, I've got a Boolean function, is there a circuit of such and such a size that computes this particular function, really is a very simple, purely combinatorial question. And that's the real virtue of all this that gets us from strange computers that seem hard to think about to combinatorics that seems easy to think about. Brackets, though in fact is extremely hard to think about. I'm going to discuss something that in the literature is sometimes called the straight line model of computation, which is actually, unless I've misunderstood something, completely equivalent to the circuit model of computation. So for the straight line model of computation, what I do is this. I take a bunch of bits, that's the input, and then I create some more bits along a straight line. And how do I do that? Well, this bit here, for each one, I'm either going to take the not of one of the earlier bits, or the and of two of the earlier bits, or the or of two of the earlier bits. So for example, if I might take the or of bits 2 and 3, in which case I'd write a 1 here. And then I just carry on. So each thing here is the and, or not of some earlier things along the sequence. Not necessarily inputs, it could be some of the ones I've already created out of the inputs. How do I get from a circuit to this? I just totally order the vertices of the circuit in such a way that each vertex comes after the ones that I used to create that vertex, using an AND gate or OR gate or NOT gate. So it's completely obviously the same model. Nevertheless, this is a nice way to think about it. Let's write a sequence of sets, E1, E2, up to En. What is EI? EI equals a set of input strings epsilon such that you get 1 in position I. So let's just quickly think about what some of these EIs are. So epsilon is the initial string of n digits. So what is E1? Well, E1 is just a set of strings that start with a naught. And E2 is a set of strings whose second coordinate is a naught. Is a 1, sorry. And E3 is the set of strings whose third coordinate is a 1, all the way up to En, set of strings whose nth coordinate is a 1. What about this one in this example here? En plus 1 was a set of strings that are either 1 here or 1 here. So we see in this particular example, En plus 1 equals E2 union E3. More generally, each of these sets here, if you write them like that, is either the complement of one of the earlier sets, that's what you get in the case of a NOT gate, or it's the intersection, which is what you get in the case of an AND gate, or it's the union, as you get in the case of an OR gate. Let's just say, we're supposing little m, was, so supposing the nth thing was the AND of two earlier things, the only way of, the set of things that would give me a 1 in position m will be the set of things that give me a 1 in both this position and this position, and therefore em is that ei intersect that ej. So another way of thinking about computation is that there's a Boolean function that we're trying to calculate, which we shall identify with the set of possible input strings that give you a 1 at the very end of the calculation. So wanting to calculate a Boolean function is the same as wanting to define some subset of 0, 1. We've got some target subset of 0, 1 to the n. That will be the set of things that give me a 1 at the very end. And that particular set, we want it to be some nice set corresponding to a function that we're trying to compute. Our inputs start off with some particularly nice sets, E1 up to En. And what are we allowed to do? We're allowed to construct a sequence of sets, starting with these sort of half spaces, and each set in the sequence is allowed to be built from earlier ones either by taking a complement of an earlier one, or the intersection of two earlier ones, or the union of two earlier ones. And I hope that by taking a sequence of that form, I can eventually create the set E. Or I'm even more ambitious, I want to prove that P doesn't equal NP. I'd like to prove that if I only go for polynomially many steps down this sequence, I actually can't create the set. And we're going to be discussing how one might be able to do that. But let me just, so the main point I've been trying to make through this whole lecture is that we've now got a rather nice set theoretic question. Start with some set E. It might encode, for example, a set of all graphs. So how do you encode a graph? Well, you've got n choose 2 possible edges. You just put a 1 for the input if that edge is in, and a 0 if that edge is not in. Supposing we want to solve the travelling salesman problem, then we would like to have a Boolean function that is 1 if the graph contains a Hamilton cycle, and 0 if the graph doesn't contain a Hamilton cycle. Equivalently, we want to pick out the set of all possible assignments of edges such that the resulting graph contains a Hamilton cycle. And if we want to show that P doesn't equal NP, what we'd like to show is that if we start with these very simple graphs, that's now an n choose 2, so EI is a set of graphs that do have edge EI in. It's this ith edge here, it does belong to the graph. So you've got those very simple sets of graphs, a set of all graphs that contain this edge, a set of all graphs that contain this edge, and so on. Can you, out of those sets of graphs, by just iterating the processes of complements, intersections, and unions, eventually build up in polynomially many steps the set of graphs that contains a Hamilton cycle? Or is there some sense in which the set of graphs that contain a Hamilton cycle is too complicated to be built up in a short number of steps from those very, very simple sets of graphs? So there you are, nice combinatorial exercise for before the next lecture. What I'm going to do is, of course nobody knows how to do that, but there's a result that looks sort of similar to that, where you don't allow yourself complements, you just allow yourself intersections and unions. Of course then, that restricts what functions that you can actually calculate, but it turns out you can calculate any function that's monotone. The monotone meaning if you change a 0 to a 1, then the value of the function doesn't go from 1 to 0. Or in terms of sets, if your set is in, if you've got some sequences in the set, then changing a 0 to a 1, you're still in the set. That's a monotone function. So you might hope that every polynomially computable monotone function could be computed by a polynomial-sized circuit that only uses and or gates. But that, it turns out, is false, and there's a way of showing that there are some, no, actually the function has this graph got a clique of size such and such, cannot be computed in polynomial with a polynomial-sized circuit using just and or gates. That's known as a monotone circuit. So that's going to be one of the main results I talk about. Actually, before I get onto that, at the beginning of next time, I do want to say a little bit, because I know not everybody is on top of this, about precisely what the question, does P equal NP, is. What is NP? What does it mean for P equal to equal NP? And how does that relate to the circuit model of computation? So it's a little bit more informal stuff along those lines at the beginning of next time. And then I will start the process of proving this result of Rasberov that says that at least for monotone circuits, you do need exponentially many gates.